Hello everyone, my name is Joshua Cass. I'm from the University of Washington, where I work with John Rare on development of theories and computational tools. And today I'll be talking about the theory and calculation of X-ray spectra with FEFF, which is a code that calculates all sorts of X-ray spectra, X-ray absorption, X-ray emission, non-resonant and resonant inelastic X-ray scattering, Compton, etc. Of course, today this is an XAFS workshop, so I will be talking specifically about FEFF calculations of X-ray absorption. So just to give you an outline, I'll start with an introduction to X-ray absorption spectroscopy. Then I'll talk about the theory of XAFS, followed by the theory of XANES. Then I'll talk about some pitfalls you can find when you're calculating things with FEFF due to the approximations that it makes. And then finally, I'll finish with some practical aspects of calculating XANES, although just a few simple things, since in detail you will be seeing this during the FEFF demo given by Fernando Vila. So what is X-ray absorption spectroscopy? This is the probability of absorption of a photon in the X-ray regime. And what happens is that a photon comes in, it hits the sample, and it kicks electrons out of the system. And in particular, if you're looking at core levels, then it kicks that core level out of the system past the Fermi level and into an unoccupied state. Now, if you're not near the binding energy of a core level, you get a pretty smooth curve, as you see for most of this range here on this curve that's for copper absorption. But right when you get to the binding energy of a core level, that core level electron is all of a sudden energetically allowed to participate in the absorption process, and therefore many more photons are absorbed, and you get a sharp jump in the spectrum, which we call an edge. And the edges have labels that correspond to the quantum number of quantum numbers of the core level. So for example, the K level, or the K edge, corresponds to the 1s level, the L1 to the 2s, the L2 and L3 to the relativistically split p states, the p1 half and p3 halves, and you can have so on and so forth, more M1, M2, 3, M4, 5 corresponding to D levels, etc. Now, if you zoom in on one of these levels, you will see that there are oscillations, and that's what we call the fine structure. And qualitatively, just very briefly, these are due to quantum interference of the photoelectron with itself as it scatters off of neighboring atoms. And we've split this into roughly two regions: the X-ray absorption near-edge structure region, or XANES, which is from about the edge to about edge plus 30 or 40 eV, and the XAFS, or extended X-ray absorption fine structure region, which is everything beyond that. And the reason for this split is basically that the interpretation becomes quite a bit easier as you get to higher energies in terms of the many body effects and things like that are involved. It's a little bit easier to calculate, and it's quite quantitative in terms of what you can extract from that curve compared to the XANES, where it's more of a qualitative calculation at this point. So in 1970, Stern, Sayers, and Lytle came up with a qualitative interpretation of XAFS, where they noticed that if you take background, subtract the edge so that you get the edge sort of isolated, and then you draw a smooth curve through the oscillatory part so you can extract just the oscillatory part of the curve, You can then Fourier transform, and you get something that looks like sort of a shifted radial distribution. It's not exactly that, and I'll talk about the reasons for that a little bit later, and you'll probably hear quite a bit about that as well in other talks. So how do we describe the extended X-ray absorption fine structure theoretically? We can start with Fermi's golden rule, just saying that the absorption is proportional to a sum over unoccupied states, and then it's a transition matrix element, where here D is the transition operator, which represents the interaction between the electrons and the photon, and basically you can interpret this as a photon creating a transition between the core level and some unoccupied level F. And then these are multiplied by an energy conserving delta function, which is forcing the change in energy of the electrons to be equal to the absorbed photon energy. Now, if you look at one of those matrix elements, you can write that in integral form in real space. And if you note that the initial state I is very localized around the absorbing atom in question, then that forces everything to be near r equals 0, or the origin. And the final state, or unoccupied state, is slowly varying around the origin. It doesn't wiggle too much, and therefore you can pull that out of the, or at least approximately pull that out of the integral, and therefore these matrix elements are proportional to the final state at the origin. Now you can take that final state and you can write it as an outgoing wave coming out away from the absorbing atom, plus a scattering wave that's coming back in. And therefore you can see that if you're looking only at psi f of 0, the oscillations will be due to the backscattering of these outgoing waves interfering at the origin. So now if you go ahead and write your squared matrix element in terms of these states, you get something that looks like an e to the I kr, and you can define the oscillatory part, or fine structure part, called chi, and you get something that might look familiar to you. You have a sine of 2kr, and it has an amplitude with it, and here we have f, which is the backscattering amplitude. So this is sort of like a single scattering XAF theory here. So 2r is, of course, the twice the bond length, because that's that's the path length, I should say. That's the path that the electron takes to the scatterer and back. Now, of course, you can have many single scattering events if you have many atoms. You don't just have one neighbor. You have different types of atoms, and so forth. And so you can get a different amplitude for each one, and you get a different backscattering amplitude. And then you have different bond lengths r sub I, and so you get a sum over these types of terms. In reality, everything is much more complicated. You have phase shifts, Debye-Waller factors, inelastic losses, many body effects, amplitude reduction factor, I should say. And then you have also curved wave scattering, because all of that was basically plane wave scattering based theory. And then you can also have multiple scattering, where you scatter off of more than one atom before you come back to the origin. So let's explain each one of these terms. Okay, so first of all, you have phase shifts. And this is basically due to the fact that the atoms are not point charges, right? And and therefore, instead of actually just reflecting directly off of the neighboring atoms, the electrons or the electron wave function has a phase shift due to the finite extent of that atom, both as it scatters off of the neighboring atom and as it enters the central or absorbing atom. So another thing that can affect the X-AFs is disorder, and that can be static disorder or vibrational disorder, for example. Static disorder could be something like defects or whatnot. Now, what this does is that instead of having a nearest neighbor that's at a specific position, you have a set of nearest neighbors which give you a probability distribution of neighbor distances. And this causes a damping factor on your on the contribution from that particular path. And if you model the probability distribution of path lengths with a Gaussian, then you find that the damping factor is e to the minus 2 sigma squared k squared, where sigma squared is the mean square relative displacement of the path in question. And so that's basically the width of the probability distribution squared. And since this is multiplied by k squared, then you can see at very low k or very low energy, either way you want to say it, you get very little effect. Whereas at large energies, you get a very large effect, large damping. Also, since this probability distribution gets wider as temperature grows because vibrations get larger, you also have what looks kind of like a melting of the X-AFs curve. At larger temperatures, the damping factor is much smaller, or much larger, I should say. The effects of damping are much larger. You can also have inelastic losses due to the interaction between the core hole or photoelectron and the rest of the system. In particular, that can be interactions between those and the other electrons in the system, causing density fluctuations, the interactions between the core hole or photoelectron and phonons or plasmons, etc. And this causes effectively an inelastic mean free path of the photoelectron, where the inelastic mean free path is proportional to the X-AFs momentum k divided by the lifetime broadening or combined lifetime broadening of the photoelectron and the core hole. And in the end, all of this causes the signal from that particular path to have an extra exponential damping beyond the Debye-Waller factors that is equal to e to the minus 2r over lambda. Now, if you stare at this lambda for a moment, you'll notice that as roughly as k grows, or as energy grows away from the edge, this gets larger and larger, and therefore you should have a smaller and smaller effect as as energy gets larger. And you can see that down here. It's kind of opposite of what you see with the Debye-Waller factors. The large effect is in the Zanes region, or at the low energy region, and the smaller effect is at the high energy region. You can have further many-body effects as well, basically due to the fact that you can have multi-electron excitations in the system, where you get satellites. What that means is that you can actually have extra peaks and things like that, but for the most part in the X-AFs, these extra many-body effects tend to just reduce the the oscillation amplitude for the paths. And this is more or less path independent, although not exactly. And you can see here, this is an estimate of those reduction factor. And over the whole range of the x-halves, it's mostly pretty constant and somewhere near 0.9 or so, although it becomes smaller in the Zanes region, at least for part of it, down at 0.8 or so, and it oscillates quite a bit, or it wiggles around quite a bit more than in the x-halves. And this kind of thing just shows that many-body effects are a little bit more important, or they're harder to model in the Zanes. Finally, you can also have multiple scattering and curved wave scattering effects. So, that first of all, when your photoelectron comes out of the atom, you can actually get it scattering off of a neighboring atom, then a second neighboring atom, and then back to the origin. And this, of course, changes the kind of function that you're going to get, although you can cast it still back into a similar type of expression where you get something that still looks like your normal x-halves equation. And if you combine that also with effective scattering amplitudes, note FEFF here, that's really what the code FEFF is named for, this effective scattering amplitude, which basically takes into account the curved wave effects on the scattering amplitudes or on the equation. And then finally, you put in all of your other things that you need to put in, the inelastic mean-free path, the Debye-Waller factors, the amplitude reduction factor, and then you also have coordination numbers, which is just how many atoms are at a particular distance of the same type. And you end up with the x-axis equation that we know. And if you then Fourier transform this thing and you phase correct, meaning you correct for these phases that you have in here, or at least for the absorbing atom and the nearest neighbor, then it shifts the curve back to pretty much the right distance. So you get the first peak at the nearest neighbor distance, the second peak at the second neighbor distance, and so on, although you can get extra effects due to these multiple scattering peaks, right? So the multiple scattering peaks you can have, for example, collinear peaks that show up or multiple scattering peaks that show up right underneath a single scattering peak. And in that case, they might, destructively interfere and you get a much smaller peak, for example, or they can just show up in places where you don't expect a peak to be based on a radial distribution function. So what I would really call this is a path length distribution function, or something along those lines. So now, if you'd like to know more about the quantitative theory of X-ray absorption, you could look at Rare and Albers. Also, there's a very good article in the book Principles, Applications, Techniques of X-halves, X-halves, and Zanes by Ed Stern. So how do we actually calculate Zanes? What is our theory here? So let's go back to Fermi's golden rule, or the Fermi's golden rule's expression for absorption. And we notice I have this sum over F, I, D, F, these matrix elements. Well, what I didn't mention before is that in reality, I is not a core level, but a many-body ground state. And F is not an unoccupied state, but a many-body excited state. And what that means is that the wave functions include all of the electrons and coordinates of all of the electrons. And since we're in a solid state system, or at least those are of interest to many of us, there are of order 10 to the 23rd electrons in the system, and it's, really is impossible to calculate anything using these many-body states. So the first thing we have to do is whittle this equation down to an effective equation or a model equation or something like that. So one way to do that is to use an effective single particle theory or density functional theory or quasi-particle theory, etc. You can go a little bit beyond that using Bethe-Salpeter equation, or TDFT, which describe a particle whole wave function or a two-particle wave function effectively interacting with the rest of the system. For small systems, you can use quantum chemistry type methods like configuration interaction or CAS-SCF. Those are, effectively exact in the sense that you can calculate things as much as you can fit on a computer. The theory is exact in principle. Now, multiplet theory is another way to go. That's more of a model type theory, and I won't really talk much about that, but that's just good to know about. Okay, so what I'm going to focus on is density functional theory or quasi-particle methods, and the basic idea here is that what was proven by Hohenberg and Kohn is that the ground state density or the ground state energy of a system, of an electronic system, has a one-to-one correspondence with its density, and therefore you can actually, if you can solve for the density of the system, you may be able to get its energy. There you can minimize then the electron energy by just knowing the density. Well, what's the use of that? Now the density of a many-body system still only has one coordinate in space. So you've gone from having a wave function that has 10 to the 23rd coordinates to a density that has only one coordinate. Three coordinates, x, y, and z. But anyway. And so the idea is that you can take that density, you can calculate an effective single particle potential that describes a non-interacting system, non-interacting electron system, where you only have to take into account one coordinate for the wave functions, or for each wave function of each electron. And then you can solve for the eigenstates of that system, and then solve for the density, etc. Okay, so there are different ways to solve for the eigenstates of the system. You can use basis set methods to solve for those eigenstates, and you can use real space grid, or you can not solve at all for those wave functions. You can solve instead for what we call Green's function. And then there are different ways to solve each of these different things. You can use basis functions that are periodic, like plane waves, or that are appropriate for periodic systems, like a plane wave basis set. And codes that do this are things like Quantum Espresso, Abinit. Vn2k is a slightly modified version of this. And then there are also things that are more appropriate for molecules that use localized or Gaussian type basis sets, things like Stobie, Orca, or Gaussian. There are also a few codes that do things on a real space grid. One of those is FDM-NES, which does full potential X-ray absorption calculations. Of course, I'm going to focus on Green's function methods because that's what FEFF does, but I will talk a little bit more about DFT methods. So how is this all of this done with density functional theory or quasi-particle methods? So generally, what you need to do is you start off with some guess for the density. You calculate an effective single particle potential, which is a functional of that density. You use that potential in a Schrodinger equation or some type of differential equation to calculate either the wave function or the Green's function. This then gives you a new density. You can calculate that from these wave functions or Green's functions easily. You can then check to see if your density is self-consistent, if the new density equals the old density. If it doesn't, then you use the new density to calculate a new potential and go back through the cycle. If it does equal the old density, it is now self-consistent, and you can move on to calculating the spectrum. In the case of wave functions, you do that with the golden rule. So therefore, what we need to do if we want to calculate absorption using Green's functions, we need to be able to calculate the spectrum from a Green's function, and we need to be able to calculate the density from Green's function. So how do we do this? Let's go back again to Fermi's golden rule. At this point, we now have single particle states, single particle effective states here, because we're using a single particle effective Hamiltonian. Now, you can manipulate this by taking these matrix elements and folding them outward so that you get ID and ID dagger on either side of things. You can pull those out of the sum, and you end up with something that's proportional to the imaginary part of the Green's function in here, this whole sum over f d delta of EF minus EI minus h bar omega. Okay, and this formula is actually one of the reasons that solving for the Green's function directly by solving a differential equation for the Green's function can be much more efficient than using wave functions. You can imagine if the final states here are continuum states, roughly plane waves, then there is an eigenstate at every energy, meaning between every energy and every other energy, there are an infinite number of eigenstates. And therefore, there are many, many eigenstates to solve if you want to go to high energies. On the other hand, if you solve directly for the Green's function, then all you need to do is plug that in. You solve it at whatever energies you'd like, the spectrum at, and that implicitly includes the sum over states. You don't have to actually do that sum explicitly. Okay, so now we have the spectrum in terms of the Green's function. We need to get the density in terms of the Green's function. So we can go back to a definition of the density, and you can prove, I won't go through it, but you can prove that that's equal to an integral over energy of the imaginary part of the Green's function. In particular, it's an integral over energies that are, you could think of as occupied energies. It's up to the Fermi level. Okay. So, how do we actually calculate the Green's function, though? Like I said, it's, you can think of it as solving a differential equation, but the other way you can think of it is that a Green's function is an inversion of the Hamiltonian, or E minus H in this case. Okay, I don't want to get into exactly what that means, but I will talk about how you can expand that. You can expand that in terms of a free Green's function that represents free traveling plane waves or spherical waves, and it's expanded about that free Green's function, and expanded in terms of the scattering potential. Now, the scattering potential is a sum over all of the single site potentials, or sum over all atoms of the atomic potentials. Now, you can split those you can split that potential into what we call single site potentials, where it's zero outside of some radius, and inside the radius it's non-zero, or outside of some, zero outside of some radius. Now, if you make a further approximation that it is spherical inside the radius, then you get what we call muffin tint potentials, which is the approximation we make. And in one dimension, it might look something like this picture down here. You have atom cores here where the potential becomes very, very low and has a singularity. And then it rises symmetrically, and then it has an in-between a potential as well. It might be zero or it might not be, and that's called the interstitial potential. Dimensions that might look something like this muffin tin here, maybe minus the delicious looking globe squash. Okay, something like that maybe. So now we have our potential decomposed into single site potentials. But it turns out that you still have some complication here. When you do this expansion, you can still have consecutive scatterings from a single site potential. You can have G0 VI, G0 VI, G0 VI, right, where you're really scattering off of the same potential many times. And you have to take that into account explicitly through the sums. On the other hand, if you define what's called a scattering matrix, then this implicitly sums all possible number of scatterings, consecutive scatterings off of the same site. And therefore, the sum collapses into pieces where if you're going to have multiple scatterings, they have to be off of different sites. So a G0T, G0T, G0, which is a double scattering, has to be scattering off of one site and then another site afterwards. Now you write all of this in a site and angular momentum basis, and this naturally separates structural and chemical dependence, where all of the structural dependence is in this free Green's function. The free Green's function knows nothing about the atomic potentials or the sites except for where they are. And that's indicated by the fact that G0 is dependent on two site labels. So it knows the distance between the sites, but it doesn't know anything about what the sites are. On the other hand, the scattering matrix only depends on the single site, I, but it depends on that I through, the element in question. And so that's where all the chemical dependence is. So then, in final analysis, we always write things, as I said, in terms of the scattering matrices. And if we keep that expansion in terms of the scattering matrices, or T matrices, we call that the path expansion, and that's directly related to the XF's equation. And you can see that by kind of looking at this and thinking, okay, well, this expansion starts with a G0, which is just an outgoing wave, therefore it doesn't have any interference at the origin, and that doesn't really contribute to the oscillations in the fine structure. The first, the second term here with the single T matrix or scattering matrix corresponds to single scattering, which you can see over here in green. In this sort of representation of atoms, you have an absorbing atom in black here, and then there could be a path, a single scattering path to the neighboring atom, and that goes to neighboring atom, scatters, and comes back. Similarly, something with two scattering T matrices, or the term with two scattering T matrices takes into account all double scatterings. So things like this red, go to a neighbor, scatter off of it, go to a second neighbor, and then come back to the origin. And of course you can have multiple scattering beyond that, like in this gray path, for example. So that's what we call the path expansion, and that's pretty much the way that FEFF calculates the Green's function, but it does more than that. It actually casts this equation in terms of the parameters that go into the XF's equation and calculates a bunch of those parameters, like the scattering amplitude and things like that, and phase shifts. so that you can use those in the XFS equation and fit the parameters that you're interested in, like bond lengths and coordination numbers and things like that. Now, for the X-ray absorption near-edge structure, or ZANES, it turns out that this expansion does not converge very well. And there are a couple reasons for this. One of them is that the T matrices at low energies, or the backscattering amplitudes, the scattering amplitudes at low energies, can be large for high angles, right? So at high energies in the XFS, they are quite small for large angles. So paths like this red path and this gray path don't contribute, because the only large components of the scattering amplitudes are backscattering or forward scattering. So you can have paths like this single scattering green path, or you can have a double scattering if it's collinear. But there aren't very many of those, right? On the other hand, if you have even a cluster like this and you include paths up to 7, 8 legs or something like that, then there are quite a lot of them. And as the cluster grows, you get a huge number of paths that can contribute. And so in the ZANES, where those paths do contribute, your convergence is very poor. The other thing that can contribute to the fact that you have poor convergence is in the XFS, you have a large effect of vibration or distortion effects, disorder effects, I should say. And those tend to grow with path length as well. And so larger length paths have larger Debye-Waller factor damping. So how do we deal with the near edge structure, or the near edge spectrum where the convergence is poor? Instead of doing a summation explicitly, we decide we're going to take a specific cluster of atoms. Maybe we just take this whole cluster here, for example, and then sum all of the paths implicitly by doing a matrix inverse. Anyway, it turns out this sum is easily transformed into this matrix inverse, and that sums all of the paths up to infinite legs. And you might ask, well, if you can sum to all order, why wouldn't you do that all the time? And well, the issue is that these matrices can be very large. They grow like the number of atoms times the angular momentum that you truncate at squared. And so the timing grows like, L to the 6th, and it grows like the number of atoms cubed. You're talking about timing to invert this matrix. So anyway, you can only do it for some certain number of atoms. Usually 100 or so is actually pretty much okay. But at certain times you might need even 1,000 atoms, for example. Okay, so now that you have an idea of the basic theory of how we calculate the Green's function, in the XFS we use the path expansion. In the ZANES we invert the matrix and use what's called four multiple scattering. Now we want to think about, well, how do we augment that, because there are some effects that we haven't talked about. So for example, the photoelectron has a finite lifetime, and this causes shifts and broadening in the peaks of the spectrum. And this is something that goes beyond theories like density functional theory, which are mean field theories. And in order to take that into account, you need to calculate what's called a quasi-particle self-energy. And this is added on to the Hamiltonian as an extra effective potential that is now energy dependent. So I won't get into too much about how to do that, or I won't get into really at all about how to do that, but how to calculate the self-energy. But it's taking into account the interactions between the photoelectron and sort of the valence density. It's creating density fluctuations as it's traveling through the material. And the self-energy takes into account those effects. And just to show you what it kind of does, you can see down here, if you have, this is boron nitride, if you have no self-energy, then you get a much sharper features in the spectrum. There's very little broadening, and there are also shifts compared to the experimental curve. When you add the self-energy, then you get more broadening, and the broadening is energy dependent as well. And then you also get shifts to the usually blue shifts, at least at higher energies. Sometimes you can get a little bit of a red shift in some peaks. Anyway, and that's the kind of effect you should expect to see from adding a self-energy or from changing your model of the self-energy. It's shifting and broadening of the peaks. Another many-body type interaction that we didn't discuss yet is the core hole interaction with the photoelectron. Basically, when the core electron is kicked out of the atom, it leaves the atom ionized, and therefore the photoelectron doesn't see a neutral atom, it sees an ionized atom. And you need to take that into account because it's going to, pull weight in the spectrum down towards lower energies. And one of the ways you can do that is through what's called the final state rule, where you calculate the Green's function in the presence of that ionized atom with the core hole in there. And there are details here. We don't just put a core hole in, we actually put the extra electron in the valence system so that the system as a whole is not ionized, but the atom still basically is. The extra electron doesn't necessarily stay right on the atom, and it certainly doesn't screen as well as having the core electron still in there. Another way you can do this is through linear response, where you calculate, you use a dielectric function to calculate the screened Coulomb potential from the core hole. And this turns out to be usually pretty similar to the final state rule. And anyway, you can see the effects of the core hole down here. They're quite large for this, which is again boron nitride. In the red, you can see the final state rule works quite well for boron nitride, whereas when you use no core hole, then you get a huge shift of weight to higher energies, or basically you lose all of the white line. So anyway, this is important to take into account the core hole effects. So now you have a basic idea of most of the stuff that goes into calculations with FEFF. I'm going to give you just a list of the key approximations, and then we'll talk about how, when and some of these approximations can break down. So the most important are probably spherical muffin tin potentials. That's hugely important approximation. It makes the calculations very efficient. Local density approximation is used for the actual density, for calculations of the density. So that could be important in some cases. The quasi-particle approximation that we use, first of all, it's an approximation to the quasi-particle self-energy, but in addition, we're using something called the quasi-particle approximation, which doesn't add extra peaks in the system. It just adds broadening and shifts to each peak that's there, basically. There are cases where you get extra peaks, and we'll talk about that in a moment. And then the core hole treatment as well is an approximation. Final state rule is not exactly correct, and there are cases where it's better to use no hole. And a better way to treat this is through beta saltpeter, but I won't really talk too much about that. So when might these approximations break down? First, you can talk about spherical potentials. The less symmetric the system is around the absorbing atom, the more likely it is that spherical potentials approximation is going to break down. Like I said before, the treatment of the core hole, there are certain cases. So, for example, in metal L edges, transition metal L edges, where you're talking about actually metallic systems, then the final state rule does not work so well, and it turns out that using no holes seems to work much better. I'm not talking about transition metal oxides, but transition metals. And then self-energy approximations. Once again, there are systems, again, like transition metal oxides that are highly correlated, and simple self-energy approximations don't work so well. So you might need to go beyond the models that we have in FEFF. There are other many-body effects beyond quasi-particle self-energy effects where you get extra peaks, like I said, called satellites. In particular, charge transfer excitations that can happen in transition metal oxides or cuprates. Also, F electron states or systems like cerium oxide. And then there can be multiplet effects. So let's just take a look at some of these in particular. Okay, so a very non-symmetric system is Br2, or any diatomic molecule would be an example of that. And in looking at this, what we mean here by not symmetric is that, this is in 2 dimensions, of course. If you imagine the absorbing atom is at about minus 0.5 here, then the potential around the absorbing atom is not symmetric at all. On the left side, it goes slowly up to 0, and on the right side, it only goes to minus 4 or so, right? And so on the left side, you have to choose an interstitial. You can choose it to be down at where the bond is, and in that case, you might represent the bond reasonably well, or electrons that are atomically bound might be in roughly the right place, but you will miss any binding that's molecularly bound, molecular states that are bound in this region. On the other hand, you could pick the interstitial potential to be at the top at 0, and in that case, you will get bound states in this region up here. But, they may be too bound because of the fact that you have interstitial in here. They may look more like atomically bound states. In any case, there isn't really a good choice for where to put the interstitial in this case. And you can see in the results here how this affects things. So FEFF tends to put the interstitial down at the bottom here where the bond is. And if you do that, then you get something that looks like a potato instead of getting a nice sharp peak in the white line. Okay, so you can also have further many-body effects that cause satellites in the spectrum or extra peaks. And in particular, you can see this in transition metal oxides as charge transfer effects, charge transfer excitations. And what happens is basically when the core electron is kicked out and a core hole is created, that sudden appearance of a core hole creates excitations of the valence electrons. In particular, the ligand electrons on the oxygen are pulled onto the metallic absorber, and they can oscillate back and forth between them. And so you get a satellite corresponding to a state where the extra electron is on the ligand, and a main peak where the state is on the metal. So here you can see the effect You take the single particle theory and you look, and it doesn't have peaks F and H, for example. And if you add the many-body effects, then those peaks show up. And if you notice, those peaks seem to be basically a duplicate of peaks E and G, shifted by a particular energy. And what's happening is that you're really getting just a reproduction of the single particle spectrum shifted by an energy that's equal to the charge transfer excitation energy. And this is just because when you create that charge transfer excitation energy, you still have to have conservation of energy, and so the photoelectron energy has to be lowered by that same amount. So finally, I'll talk a little bit about how we interpret Zanes. Zanes is sensitive to the unoccupied local density of states, or angular momentum projected density of states. It's also sensitive to symmetry and charge transfer or oxidation state. And finally, you can get things like occupation of spin occupation or orbital angular momentum occupation from the L edges. So one of the things you can calculate with FEFF beyond spectra are what's called angular momentum projected densities of states. And these are important because they give you an idea of what the eigenstates of the system look like, or how they're hybridizing and things like that. It can give you that idea. And they have a one-to-one correspondence with the peaks in the Zanes, pretty much. And this comes from the fact that that most of the spectrum is dipole limited. What that means is that if you go back and think about the Fermi's golden rule expression, it has these matrix elements where D is the transition operator, and to a good approximation for most of the spectrum, except for maybe in the pre-edge, the dipole approximation is appropriate. And this means that the angular momentum L has to transition to L plus or minus 1. So if you're looking at a K-edge where the initial state is, or the core state is a 1s state, then it's going to transition to P states. And this angular momentum projected density of states gives you, the amplitude of states at each energy. And so that's exactly what you see in the Zanes, except that it's cut off at the Fermi level. So it's only unoccupied states. And you can see there is a one-to-one correspondence between the peaks. They are shifted and broadened because of self-energy effects, but pretty much they're very similar. And you can also look at the XES, X-ray emission spectroscopy, and that will give you a measurement of the occupied states, since XES is occupied states falling down into the core hole and you're measuring the outgoing photon. Like I said, right near the edge or in the pre-edge, you can have quadrupole excitations where you go from L to L plus or minus 2 or to L. And this is important. This can be particularly important in D or F states, state systems, where if you're going from a K edge, you may have a very large density of states right near the pre-edge that corresponds to a large peak in the D states. And if you can go from L to L plus or minus 2, then that will show up as a small peak there. You can also interpret the angular momentum density of states in terms of hybridization between different orbitals. You can look at ligand LDOS as well as the absorber LDOS, or you can look at F and D DOS, and you can see where peaks coincide, and this means that there is some hybridization between states at that energy. And I believe these two peaks, for example, here in the DOS correspond roughly to this peak in the spectrum. And you can see that this is in this EU203 system, the DDoS and the FDoS in this case are hybridized a little bit, not a huge amount. Mostly this is actually an F state. So even though, this is L3 Zanes, so you're going from P state to D states, even though you're going from P to D, and this is really a dipole allowed transition, your state that you're going to is nominally an F state. It's mostly F, although you're only coupling to the D portion of the state. Similarly, you can look at things like this for the ligand hybridizing, the ligand states, say, of the oxygen, for example, in this case, hybridizing with the absorbing atom states. So you can also have effects of symmetry on the Zanes, and they can be quite large, especially in the pre-edge region, but other regions as well. And in this particular case, you can see that as you go from two neighboring oxygens on a calcium, we're looking at calcium in solution, and if you go to 2 or 4, you have this pre-edge peak, and once you go to 6 or 8, you basically get a situation where hybridization of the orbitals is not possible due to symmetry, and you don't see that peak anymore. This is also important because modeling distortion can cause this peak to come out. So we can see that in a moment. In this case, that's particularly true. This is barium titanate, and basically you have very little pre-edge peak in the symmetric case, which is the dashed line here. Whereas if you distort the system, then you all of a sudden get this pre-edge peak. Obviously, the energies of the pre-edge peak is a little bit off compared to the experiment. This is most likely due to full potential effects, which tend to be a little bit larger in the pre-edge region. But anyway, this is a case where you need to have the distortions in the system in order to get the correct pre-edge peak, because the excitations to that orbital, or the hybridization of that orbital with the p states in this case, are forbidden in the symmetric system. This can also happen. This distortion in this case is static distortion. It's like an octahedral system with the central atom shifted. But that distortion can be caused by vibration as well. And so taking into account vibration can be important in these pre-edge cases. The small peaks might show up if you average over molecular dynamics configurations, for example. Another way you can analyze Zanes is to correlate the edge position with the charge transfer in the system, and that could be oxidation state, or it could be just electrons transferring from an interface to some, say, metallic nanoparticle, for example. And the physics behind this is there are actually two kinds of effects that you can have. One is that you have the Fermi level here, and so unoccupied states are to the right. If you transfer electrons onto the system, the Fermi level shifts to the right because more states are occupied, and that shifts the edge upward in energy. On the other hand, as you transfer electrons to the system, they screen the core hole, and if you have more screening of the core hole, then this causes the energy of the core hole to shift upward, and therefore the edge, which is the difference between the Fermi level energy and the core energy, will shift downwards. And here you can see this. You have the oxidized system in reduction here is shifted to the right, and the reduced with more electrons is shifted to the left. So that's the basics of how you might relate the Zanes or interpret the Zanes experiment by calculating things with FEFF. So you're going to hear a lot more about this, but I'll just briefly go over what it takes to simulate Zanes with FEFF. The basic idea is that you have some input structure. You need to have coordinates, species, vibrational character possibly, and that's the input for a Zanes calculation or an XAFS calculation in FEFF. There are some important options for Zanes calculations. Like I talked about before, self-consistent potentials can be important, especially for the Zanes. Core hole treatment is very important for the Zanes, and the self-energy options are important. You also want to think about convergence, and I think Fernando Vila will go over this later. When you're thinking about doing a full multiple scattering calculation, you want to think about how many atoms you want to include in your cluster, and that's true for the self-consistency loop as well, because you're using a cluster to calculate the Green's function during that self-consistency loop, and then you're calculating the density using that Green's function. And then finally, you want to think about the maximum angular momentum you're going to use. So I won't get into any more of that. One other thing you might want to look into when you're doing calculations of, especially of Zanes, is to use DFT to augment FEFF. And there are different ways to do this. You can find possible structures by optimizing the structure in DFT. You can check full potential effects. You can calculate the densities of states both from FEFF and from a DFT package, so that you can compare, and then you can fix things like the Fermi level in FEFF if that's a little bit off. You can also find chemical shifts that way by aligning the densities of states. And then finally, you can find dynamical properties like the Debye-Waller factors, where you can calculate ab initio Debye-Waller factors using a phonon calculation. And also you can do dynamical properties in terms of looking at many body effects. So anyway, in conclusion, I hope you have seen a reasonable amount of theory of XAFs and Zanes. You should now kind of get an idea that XAFs is quantitative and can be used to extract things like bond lengths, dynamic structure, Debye-Waller factors in particular, and chemical species from experimental data by doing quantitative fits to the data. Zanes, on the other hand, is more of a thumbprinting type of technique. The calculations are semi-quantitative, but you can rule out certain structures by looking at the Zanes, for example, or at least you can point towards a more likely structure, and they're sensitive to different things than the XAFs. So, for example, they're sensitive to electronic structure, more sensitive to the chemistry of the situation, or oxidation and charge state, and they're sensitive to symmetry in ways that XAFs is not. It's usually only sensitive to the coordination number, not the symmetry of the neighbors. And if you'd like to read a little bit more about advanced theory, you can look at our paper in PCCP. So thank you for listening. And also I'd like to thank the RARE group, as well as our collaborators who are probably in the audience. And a special thanks to Anatoly Frankel for setting all of this up.